Good morning. Oh, wait, one more minute. Uh, Hey, Mr. Bugs. Mr. Bugs, you want to come on camera here? Mr. Bugs. Mr. Bugs on camera. Hey, Bugs. What's up, dude? What's up? What you doing, man? Are you a little bip dog? You go bip, 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 bip. Bip, bip, bip. Okay, see you later. All right, let's start. Okay. So, SL 322. All right. So what we're going to be talking about today. So last week we were kind of talking about electrons. Okay, so the electron cloud around the nucleus, energy levels changing, photons being emitted and absorbed. And then I guess on the second lesson last week we started talking about radioactive decay. All right. And so we have what I want to introduce is some notation for describing a nucleus. All right. So let's talk about describing a nucleus. So what we do, the way to describe a nucleus is you write it as ZAX. All right. So Z is the atomic number. All right. Also known as the number of protons. Okay. So that's the number that's written down here. And as we know, the number of protons is what determines the element that we have. Okay. So X is the symbol for the element. Element with Z protons. So, it could be Fe or, I don't know, Pb, etc. Okay. Note that it is not, because the number of protons determines the element. It's not really necessary to. So the symbol is just there to remind you what that element is, but you don't really need both of these, right? Because one tells you the other. So it's a little bit redundant, but that's just the standard way of doing things. Okay. And then A is called the nucleon number. So what is a nucleon? A nucleon is a particle in the nucleus. All right. So that could be a proton or it could be a neutron. So that is what is meant by a nucleon. Okay.
What was that noise, Mr. Bugs?
So a nucleon is a proton or a neutron because those are the two particles that you find in the nucleus. It is also called the mass number because the number of nucleons is basically what determines how heavy the nucleus is. All right. Protons and neutrons don't have quite the same mass, but it's really, really close. And so basically, if you know how many protons and neutrons you have in there, you're going to know approximately what the mass is of that particular nucleus. Okay. So let's talk about, for example, carbon. All right. So carbon has the symbol C. Carbon has atomic number 6. And it has 12 nucleons. Carbon 12. All right. So what does this mean? Well, we've got 6 protons. We've got a total number of nucleons of 12. All right. And so what that means, so we've got 12 nucleons. So what that means is that there are 12 minus 6 equals 6 neutrons. All right. So basically, the number of neutrons is going to be equal to A minus Z. All right. So basically, if the particle in the nucleus is not a proton, then it is a neutron. So you got to subtract the bottom number from the top number to get the number of neutrons. So let's take, for example, uranium 92 235. Uranium 235. So this would have a number of neutrons. It would have 92 protons. And then it would have N equals 235 minus 92 equals what? 130, 142? Or 143? I think that is. 143 neutrons. All right. But here's the thing. It's still uranium. So there are what are called isotopes. An isotope has the same number of protons but a different number of neutrons. Okay, so this is actually, if you ever have heard about uranium refinement, this is the isotope that is used in like atomic bombs and in um, nuclear reactors and stuff like that. But in nature, you much more often find uranium 92 238. So this version of uranium that is more common has 3 more neutrons than uranium 235. So different isotopes of an element have different abundances in nature. Okay, this is the most common one. So what they do when you're refining uranium is you are basically extracting. So you have a sample of uranium, and you extract the 235 uranium from the sample, which has a mixture of different isotopes. Okay, and so that process makes this is what originally kind of like this is kind of the limiting step in the rate of production of atomic weapons, right? Because if you can't produce enough uranium 238, then you don't have enough to make the bomb. So they have all these, sites that were basically manufacturing uranium 238 around the clock. Okay, and it's really hard to manufacture this, or uranium 235 around the clock. Excuse me. It's really hard to manufacture this stuff. So it's like if you have a kilogram of uranium 235, it's like a lot of work got put into that. Okay. So some other examples of isotopes are carbon-14. All right. So a lot of times you'll hear the isotope just by giving the mass number. So this is called uranium-235, for example. So you could write it like this, or I could say uranium-238. Or here I could say carbon-14. Etc. Okay, so that's just another way of saying the same thing. This, of course, is going to have 8 neutrons as opposed to 6 neutrons for the standard form of carbon. This is the most prevalent form found in nature. Okay, so yeah, this is an isotope of carbon. If we talked about helium, well, the normal hydrogen, excuse me, has 1 proton and 0 neutrons. Okay, so it's just H11. So this is basically a proton, right? Because it's has 1 proton and 0 neutrons. Okay, but there are other forms of hydrogen that are found in nature. Okay, so there is hydrogen with a proton and a neutron, so 1 of each, which is called deuterium. Okay, so that's an isotope of hydrogen. And then you also have hydrogen with 2 neutrons. So it has a mass number of 3. So you have 2 neutrons, 1 proton, and that is called tritium. Okay, so you know the chemical formula for water is H2O. If the H's in the water are deuterium or tritium, then it is called heavy water. all right, because you're adding extra neutrons into the hydrogen, the water is actually heavier than normal water. That's why it's called heavy water, okay? Because it has extra neutrons in the hydrogen part of the water molecules. So it's heavier. So basically the chemistry is determined by electrons. Okay? When you guys studied chemistry, you are basically studying the physics of electrons moving around and jumping between atoms. Okay? So chemistry is determined by electrons. And how many electrons are going to get attracted to a nucleus? Well, the electrons get attracted until the number of electrons, okay, electrons are going to get attracted until the number of electrons is equal to the number of protons, okay? So the chemistry is determined by the number of electrons. The number of electrons is determined by the number of protons, Z. So that is why when we change the number of neutrons, it's still considered the same element, okay? Because you have the same number of protons, which means you're going to have the same number of electrons, which means you're going to have the same chemical properties, okay? So isotopes, so different isotopes of the same element have approximately the same chemical properties, but not quite, okay? So the presence of those neutrons, those extra neutrons or not enough neutrons, actually changes the energy levels of the electrons ever so slightly, okay? So we can measure a chemical a difference in the chemistry, but it's slight. You're going to have a huge change in chemistry if you add a proton, right? Because if you add a proton, then you are adding an electron to the electron cloud, and so you have these different shells of electrons, and so you're adding shells of electrons, and so that really changes the chemistry. But adding a neutron changes it only slightly. Okay, so if you drank heavy water, a bunch of heavy water, I don't even know how much you have to drink in order to not function anymore, but basically your body is a finely tuned machine. Your body is counting on the energy levels of the electrons in water to be where they are. And so if you were to drink only heavy water, at first you would be fine, but as that heavy water gets incorporated into your body is expecting those electron energy levels to be at certain spots, and if they're not there anymore, okay, then you're going to stop functioning the way that you did before. Okay, so if you drink too much heavy water, you will die. I'm not sure how much it is, but it's we should look that up. So anyways, yeah, different isotopes have approximately the same chemical properties, but not quite. So if you have a finely tuned machine, and it won't work with an isotope, but it's in general kind of the same. All right. So let's talk about nuclear reactions. Okay. So what if I had uranium, let's say uranium-238, and I'm going to be just making up reactions. You know, in nature, only certain reactions are occurring. But I'm just gonna, just to help with understanding the ideas, I'm just gonna be making up reactions that don't really happen. Okay. So what if uranium spit out an alpha particle? All right. Well, what is an alpha particle? Remember, an alpha particle is a helium nucleus. And a helium nucleus has 2 protons and 2 neutrons. So an alpha particle is 2, 4, like that. Okay? All right? So how could we figure out what this question mark is? So, by the way, this process would be called alpha decay. And so the way it works is that charge, electric charge, has to be conserved. All right. And furthermore, mass number has to be conserved. All right. So if you undergo alpha decay, basically the bottom numbers on the right-hand side has to equal the bottom numbers on the left-hand side. Okay. So so that signifies conservation of charge. Well, the alpha has a charge of 2. The charge on the left-hand side is 92. So what that means is that this unknown nucleus has a charge of 90. Okay. And then the total amount of protons and neutrons has to also stay the same. So that's the conservation of the upper numbers. And so this would have to be 234, because 234 plus 4 equals 238. So basically the numbers on the top have to balance and the numbers on the bottom have to balance. So this is conservation of mass, or I should say conservation of nucleon number more exactly. And this bottom row represents conservation of charge. And I don't even care what the identity of that is, okay? It's some element. I'll just call it question mark. So that is called alpha decay, when you spit off an alpha. All right? But you could have other types of decay processes. So you can have what's called beta decay. All right? And beta decay means you spit out a beta particle. Okay? Now, spit out a beta particle. So there were actually 2 forms of the beta particle. There was beta minus and there was beta plus. So the identity of the beta minus was an electron. Okay. And then the identity of the beta plus was the antiparticle of the electron, which had 2 names. You can call it an anti-electron, or you can call it a positron. Okay. Now, what is the nucleon number of an electron or a positron? Well, remember, it only counts as a nucleon if it's a proton or a neutron. Okay. So that means that beta particles have a nucleon number of 0. All right. And then the charge So Z is the atomic number, or it's the number of protons, or we can think about it as just the charge of the nucleus, charge number. Okay? Now an electron has a charge of -1. A positron has a charge of +1. Okay? So you can almost think about the electron as having an atomic number of -1. Okay? So let's suppose that we have uranium 238, and what if it beta decays? What if it beta minus decays? So it spits out a beta minus, okay, and then something else. Well, what would be the charge of this thing? It would have to be 93, okay, because 93 plus -1 is 92, all right? So the charge number, the atomic number is 93, and the mass number would be 238, because 238 plus 0 is equal to 238, all right? So that's for beta minus decay, but here's the thing. There's one tricky thing, which is that there's an additional particle that is produced in beta decay, which is called a neutrino. So in beta decay, don't forget the neutrino. Okay? And I'll talk about what a neutrino is in a second. But remember, an electron is considered a particle. Okay? So whenever you have a particle, a beta particle appears, because a beta particle is considered a particle as opposed to an antiparticle, it comes out with an anti-neutrino. So an anti-neutrino. So this is actually if you put a bar over the top, that's an anti-neutrino. Okay? So they come in pairs. You have a particle and an antiparticle when you have beta decay. All right? We could also have beta plus decay. So you have 238, 92. And if you beta plus decay, then you get a beta plus, which is +1, 0. And then you get a question mark. By the way, neutrinos are 0, 0. They have no charge and no mass number. So they don't disrupt the balance of the nuclear reaction. All right? -1 plus 93 plus 0 is still 92. 0 plus 238 plus 0 is 238. All right? So this would have to be 91, because 91 plus 1 equals 92. And this would have to be 238, because 238 plus 0 is 238. All right? Now, a beta plus particle is considered an antiparticle. So electron is a particle, positron is an antiparticle. So an anti-electron comes out with not an anti-neutrino, but a regular neutrino. Okay? So that's a little bit confusing. You have these two types of neutrinos. You have neutrino and antineutrino. And basically, you're going to have a particle and an antiparticle come out in beta decay. So that is an important little thingy. So what is a neutrino? A neutrino is a particle that is produced. Basically, what's happening in this is when you have beta decay, you have a transformation from a proton to a neutron or vice versa. Okay. And in the process of that, the electron gets spit out. And this process is governed by a fundamental force of nature called the weak force. And the weak force produces neutrinos. Neutrinos are really mysterious particles. They have almost no mass, they have almost no charge, and they interact with almost nothing. If you had a neutrino gun and you were like shooting neutrinos at a block of lead, that block of lead would need to be 1 light year thick in order to have an appreciable chance of stopping the neutrino. Okay, so neutrinos are really weird because they have almost no mass, they have no charge, and they don't interact with anything, hardly anything. So there's a famous quote about them, which is, "Who ordered that?" So it's kind of like, why do we have neutrinos? Why? For a while, we thought that neutrinos could be dark matter. They don't have the properties of dark matter, but they're kind of similar to dark matter in the sense that it's everywhere, but we can't detect them very easily. The sun produces neutrinos in copious amounts because there's beta decay happening in the sun. So the sun is blasting out neutrinos all the time, and those neutrinos are just passing right through us without interacting with us. Okay, so you actually have billions of neutrinos passing through you right now per second, just constantly from the sun. We all do, but they hardly ever interact with us. You might have had a couple of neutrinos actually interact with a molecule in your body within the course of your lifetime. You can also have something called electron capture. Okay, so electron capture actually has the electron as a reactant, not as a product. So you have a beta minus. Okay, so you're capturing an electron. All right, and so we know that 92 plus -1 is going to be 91. So the unknown is going to be 91. And then you have 238 plus 0 is 238. So that's called electron capture. So basically what you've done is you've turned a proton into a neutron. Now, if we look at this, we have a particle, an electron, as a reactant. So we have to have a particle as a product. So this has to be a regular neutrino. All right. So anytime electrons are emitted or absorbed, or positrons are emitted or absorbed, you have neutrinos that are sort of coming along for the ride. Okay. And the rule is that the number of particles minus the number of antiparticles has to be the same on both sides of the equation. Okay. So because a particle is going into this reaction, a particle is coming out. But if I had something like beta minus decay, or positron capture, excuse me. So 92 plus 1 is 93. Okay, because this is an antiparticle, then on this side I would have an anti-neutrino. Okay. All right. You can go similarly through. You can also do you know, same analysis for proton decay. Now, beta decay is the only one that involves neutrinos. These other ones don't. But proton decay, gamma decay, neutron decay. So what is a neutron? A neutron has no electric charge, and it has one mass. Okay? A gamma has no charge and no mass. A proton has a charge of 1 because it is a proton, and then a mass of 1. So you can balance reactions with neutrons, gammas, and protons as well. Okay? There's something called fission, which is when a nucleus breaks apart into substantially pieces. Okay, so if we think about all these other types of decay that can happen, just a small particle breaks off. So it's almost like you're whittling away at the nucleus, all right? But occasionally with certain radioactive elements, you can have the nucleus breaks apart into two big pieces, okay? And so when that happens, that's called fission. So the most famous example is uranium-235. Uranium-235, 92. And basically it needs a neutron to help it. A neutron will help it decay. All right. And I mentioned that when we were talking about nuclear reactors, that the neutrons are what makes critical mass happen. So basically, uranium takes a really long time and has a really long half-life on its own. But if it gets hit by a neutron, then it will decay much faster. Okay? And so when it decays, so it absorbs this neutron, the nucleus becomes unstable, and then it actually spits out 3 neutrons. Okay? And then it becomes barium and something else. So let me check the... So it becomes barium 56 141. Okay? And then, so we can see that it went from 92 to 56. So it really lost a big chunk of itself. Okay, so let's try and figure out what is the charge of this question mark. Okay? So the lower numbers have to add up on each side of the equation. So I have 0 plus 92 has to equal 3 times 0, because there's 3 neutrons, plus 56, plus the atomic number of the unknown. So that is going to be what? 30, should be 36, right? 36. So that identifies the element as I believe it's Yeah, krypton. All right, krypton is a noble gas. And then for the mass number of it, we have 1 plus 235 equals, now on the right hand side we have 3 neutrons, so we have 3 times 1 plus 141 plus the mass number of the unknown. So I have 233 minus 141, which is 92. Okay. So this is 3692. So we can see we have 2 substantially sized products from that reaction, and so that would be called fission. All right. You can also have fusion, where you have particles being added to a nucleus. I did want to just talk really briefly about another vocabulary term, which is called nuclide. A nuclide is just a particular nucleus. So sometimes you might hear me use the word nuclide, and that just means a particular nucleus. All right. So what was the objective for today's lesson? The objective is for you to be able to balance nuclear reactions. And so just to summarize, the sum of the A values of the reactants has to equal the sum of the A values of the products. And so this is conservation of nucleon number. Okay. And then you have to have the sum of the charge of the reactants has to equal the sum of the charge of the products. And this is conservation of charge. And so basically you should be able to use these laws to find an unknown product in a reaction. And the other tricky thing is the beta decay. You need to know whether it's a neutrino or an antineutrino that comes out. Okay? So that is my lesson for today, and I will see you in the Zoom.